So I'm back again. It's my distinct pleasure and honor to introduce our next keynote speaker, that is Scott Shenker. Scott has been in the field of networking almost seems like forever. He's a professor at University of California, Berkeley, has done lots of very, very good work, and as a result, has gotten lots of very prestigious awards, SIGCOMM award, and he's fellow of ACM, IEEE, and all of that. Okay, so you can read his bio about that. But today, Scott is going to talk about the wisdom of abstractions and interfaces. So I thought I will use that particular abstractions and interfaces to describe Scott as I see him. Okay, so here is my interface with Scott. An abstraction. I send an email 11 p.m., 3 a.m., 4 a.m. and a minute later, if the email is worthy of a response, I get it instantaneously. Okay, a response. Now you will say, okay, there are grad students and postdocs that are workaholic, they also work late night. What is the big deal about Scott? Okay. Then once in a while I send him a very poor text. Okay, I'm not gifted with writing text, and you get a beautiful text back. Okay, then you say, oh, what is the big deal? There are very good editors, there are lots of people who can do that. Okay, then another abstraction or interface is you send him a poor idea. Okay, he will turn it into a great idea, and then you wonder whether this was your idea. But because the idea is so good, you want to have an ownership of that idea as well. Okay, so you continue to do that. Then you think maybe Scott is only driven by stimulus. You send him something, he responds, but that's not really true either. He has generated many, many good ideas, as I said, over the years. He has created, he started work in packet scheduling and so on, led to a lot of work on integrated packet switching and all of that in the context of IETF as well, DHT-based distributed systems, data-oriented networking, and then of course, as you heard, he has been co-advisor of my team and has been participating in OpenFlow and SDN. He contributed to also this whole architecture about SDN, network operating system, and so on. And he's also co-founder of Nicira. So until he did Nicira, he was a great scholar, a great researcher, a great professor, but now he's also an entrepreneur. Okay? So with that, again, it's my great pleasure to introduce Scott, who is going to talk about something like past of the protocols and future of networking, or future of networking and past of the protocol. Okay, Scott.
Thank you, Guru. That was actually a quite entertaining introduction. So, as Guru said, actually I'm waiting. Okay, so I am going to talk about the future of networking and past protocols, and it's a joint work with Martine, obviously Temu, Nick, and many other people. As Nick and Martine had on the slide, there are dozens and dozens and dozens. So we're all gathered here today to talk about software-defined networking, and I think it's pretty clear consensus that software-defined networking, or SDN, has advantages over the status quo. That's not really what we're debating. But the question that's in many of our minds is is this somehow the right answer, or is this some stopgap that we're going to believe in it for a couple of years, and then 4 or 5 years from now, there's going to be another idea that's going to sweep the thing, and the Guru and Dan are going to organize another workshop on something else. And so the question is SDN the right solution? Is there some fundamental sense in which this is the right answer? And so my talk is not going to be about what SDN is, about why it is. It's why we ended up here. And so remember when Dan opened up this conference and he made some slightly derisive comment about the philosophy of SDN? That's me. That's what I want to talk about. How we ended up in this place, and I hopefully will argue that it is the right answer for some fundamental reasons. But before we do that, let's remember what made networking so great, in particular what made the internet so great. So it's really layering. We could build applications on top of reliable transport, on top of best effort global delivery, which is on top of best effort local delivery, which is on top of physical transport of bits. Okay, we all know that, right? And we knew that in the first time we took networking. So why is it so important? It's important because it decomposed the delivery into these fundamental components. If you sit down and you actually think about, okay, how do I actually get bits from here to there? You will rediscover that, actually the layering gets it exactly right. These are the fundamental components you need to think about. And so what do those fundamental components give you when you break up the problem that way? It enables innovation. It enables innovation. You can innovate in separate pieces of the architecture independently, but keep a coherent system. And just to dial to the end of the talk, when Martine described the value proposition for SDN, it's all about innovation. That's what the value proposition of the internet was. That's why this technology took over, is because it enabled innovation. So it was an amazing success. However, and this may not be of concern to most of you, it is to me, it is an utter academic failure. We built an artifact, we did not build the discipline. So there's no denying that the internet and networking in general has changed the world. However, when you think about it as an academic discipline, as a thing that we study, it does not match up against the other fields of computer science. If you compare it to operating systems or databases or distributed systems, in those fields, you teach basic principles. You know, fundamental results of distributed computing and Paxos and Byzantine agreement. In networking, all of us, we teach a big bag of protocols. We try and make it entertaining, but we have no principles to teach. The other systems, computation and storage, they're easily managed, largely because of virtualization, that we know how to manage them. Networks, I don't think I need to say anything more. And then, you would say, well, software systems, operating systems, so they're so widely deployed, how can they continue to evolve? But they do. We've had Ruby on Rails, we've had Apple's iOS, we've had Android. There have been major changes in the last 10 years in software systems that it's actually, when you step back, it's remarkable to think for as many devices that have software on them now, you would have thought that they would have had hardening of the arteries and been slow to innovate. But they're trucking along. They're continuing to innovate much faster than networking is. So when you look at this, you wonder, so why is networking lagging behind? What is it about networking? We have a large community. We have a very large networking academic community. We publish more papers than anybody. So why are we not able to get our act together? So to think about this, let's go back, and this is retracing some of the history that Martine described. The networks used to be very simple. IP is an incredibly simple protocol. Ethernet is a beautifully simple protocol. What could be simpler than this? But then we started to get, because of the success of networking, we started to get all these new control requirements, that all those fields that Martine talked about, the sort of this state that we had to manage by hand. We had all these control requirements that led to a great amount of complexity. And that's where we went off the rails. Now, fortunately, the infrastructure still works. I mean, I'm not complaining about how networks work today. They work just fine. But they work because you, not me, this is not my skill set, but your skill set, have terrific at mastering complexity. You talk to somebody who operates a network, they can drill down to the lowest levels imaginable. It really is quite startling how much you have to keep in your head in order to keep a network working. So our field excels at that. We know how to master complexity. But that is both a blessing and a curse. Okay. So let me tell you a simple story about complexity to illustrate why it's both a blessing and a curse. So my first non-academic job was working at Xerox Palo Alto Research Center. And I joined Xerox PARC in the mid-'80s. And at the time, it was the mecca of user interface design. Sort of PARC, not me, well before I got there, but PARC invented all the sort of personal computer, the user interfaces, and so forth. So it was the mecca of user interface design. And in around 1985, Don Norman, who was a user interface expert, probably the most famous person at the time, I think he worked at Apple then, came to visit PARC in around 1985. And so there was a lot of excitement at PARC. Here was the person who sort of made these ideas, made them sort of enter the marketplace successfully, coming to PARC to talk about it. The auditorium was absolutely packed. And so Don Norman, who sort of was a very distinguished looking gentleman even back then, sort of knew how to do a stagecraft. And so he keeps us waiting in the audience for a while. And then he slowly walks out on stage. And he walks to the podium. And we're all just waiting to hear what he has to say. He says, "Who here drives a stick shift?" So we all look at each other like, what? And he says, no, I'm serious. Who here drives a stick shift? Raise your hands. And so a few of us raise our hands, and then more and more. You know, it's an engineering audience, so we're really proud that we drive a stick shift. So pretty soon, 80% of the room's got their hands up. And so he just calmly looks at us, and he raises a finger and says, none of you should ever design a user interface. So, what was his point? His point was that the ability to master complexity, meaning drive a stick shift, is not the same as the ability to extract simplicity. And that's what you do when you do a user interface design. Now, when you're first designing a system, mastering complexity is necessary. You got to do it. Everybody thinks it's valuable. That's right. But when you're trying to make a system easy to use and easy to understand, that's about extracting simplicity. And the point that he was driving home that day over and over again was, you will never succeed in extracting simplicity if you don't at least recognize that it's a different job than mastering complexity. So if you like driving a stick shift, don't you design user interfaces, get a different job. Because you like complexity. So you don't want to design systems for people who don't like complexity. So that was his point. So why am I telling you this story? What's my point? So my point is that while networking has done many great things, we have never made this important distinction between mastering complexity and extracting simplicity. And because we've never recognized the distinction, we've never made the transition. We're still mastering complexity. The people who understand complexity the best are the kings of the hill in our kingdom, right? And we don't put much emphasis on extracting simplicity. And, that has practical ramifications, which I'll talk about, but it also has disciplinary ramifications, which is extracting simplicity is what builds the intellectual foundation. If you talk about the principles that these other fields have, they're all about having boiled the problem down to its sheer essence and then being able to describe it. We don't do that in engineering. We don't have those principles, and it's because of this. So what are other fields that have made this transition? So let's take a simple example of programming. Programming has been terrific at starting off its roots, machine languages. My God, if there was anything that was about mastering complexity, this was it. And then we developed some higher level abstractions, operating systems abstractions and so forth, that we have modern languages that have object orientation and so forth, much higher languages, much more simple to program. So the essence of extracting simplicity. And the lesson we learn here is that it's really these abstractions that are key to extracting simplicity. It's the abstractions they used in programming, and it's going to be the abstractions that we have to use in networking. Now, many of you might have heard this talk by Barbara Liskov, the Turing Award winner. She goes around giving a talk on the powers of abstraction. And she has this pithy saying, which is, modularity based on abstraction is the way things get done. Which translated means, we as a field have one trick, which is if we want to build a system, we use abstractions which lead to modularity. That is, we define some abstractions, that leads us to some interfaces, those interfaces lead us to a modular system, and it's only by having a modular system we can write a system of tens of millions of lines of code and actually get it to work and maintain it and reason about it. This is the trick we have. This is what keeps us all in business. So the question is, what about the abstractions in networking? What can we do there? So I started off the talk by talking about the great abstractions we have, which is layering. But layers only deal with the data plane. And as Martine described, where we got into trouble was in the control plane, all these control requirements. We don't have abstractions. We don't really have any systematic way of thinking about that state. The same way we do have about thinking about data delivery, we don't have about managing control state. So how do we find those abstractions? It's very simple. This is what you always do when you're charged with finding abstractions, which is you define the problem and then you decompose it. So our problem is network control. So how do you define that problem? It's pretty simple. What do you do when you're trying to control a network? You are trying to compute the configuration, that is, meaning the state, in every physical device. That's forwarding tables, that's ACLs, whatever. That's the control problem that Martin described. Right? Now, we can't do it in a fully general sense. We have some constraints. We have to realize that we operate without communication guarantees. I mean, it's our own network that's doing the communicating, so we can't rely on it being perfectly reliable. We have to deal with delays, we have to deal with drops. We also have to live with the constraint that we have a given network level protocol. If your protocol, like IP, doesn't have a packet header for the thing you want to communicate, you're out of luck. You have to live within the limitations of what the fields in the packet header are. So this is what our field has been doing for years. And we just think, okay, this is our job. And we think that way because we're good at mastering complexity. Because only people who love complexity would find this to be a reasonable request. Everybody else in the world, if you pose this question, would say, you are absolutely nuts. Let me give you an analogy to convince you. Let's take a programming analogy. I'm going to go up to a programmer and I'm going to say, please, you have to write a program that specifies where every bit is stored. That's a little bit like telling me what every forwarding entry is in the network, everywhere. You have to do it, and you have to explicitly deal with all internal communication errors. That's like we have to deal with arbitrary delays and drops in our distributed systems. And you have to do it with a programming language that's not very expressible. We're going to give you COBOL. Okay? So, if you gave that to a programmer, the programmer would immediately say, no. Say, first, let me redefine the problem. I'm going to define a higher level of abstraction for memory, so I don't have to worry about where the bits are. That's subsystem level. And I'm going to define some reliable communication primitives, so I, as the programmer, don't have to worry about that. And by God, I'm going to define a more general programming language. Okay? That would be the first thing a programmer would do. Say, I'm going to redefine the problem. And then once you've done this, this is introducing 3 abstractions. And once you've introduced these abstractions, you've divided the problem into tractable pieces. You can define reliable communication protocols. You can define abstractions for memory. And once you've done all that, you make the task of writing the control program easier. It's not trivial. If your control program was to, compute k-shortest paths and only have certain kinds of overlaps, it might be a hard computation, but it's inherently hard. It's not made more difficult by having to keep track of all the communication errors and so forth. So that defining these abstractions are the way you get rid of these extraneous difficulties, and you're only left with the inherent difficulty of the problem at hand. So now let's apply this to networking. So we're going to go from the requirements that I talked about in the control group to the necessary abstractions. So the first one is we have to operate without communication guarantees. That means that we have distributed state and that we have to somehow deal with it without having any guarantees about the communication. What that means is we need, in order to not have to, for us to worry about it, we need to define an abstraction for distributed state. So the programmer doesn't need to worry about it, we've got an abstraction for that. The second thing is we need to compute the configuration of every physical device. That's our fundamental problem. So we need to come up with an abstraction that simplifies that so that we don't need to think about every device. We just can think at some higher level that makes it easier to specify the behavior we want. And then we have to operate within a given network level protocol. And there, we need an abstraction that gives us a generalized forwarding plane rather than some specific forwarding model that was given to us. Okay? So these are the 3 abstractions we need to face. So let me talk about them briefly one by one. So the distributed state abstraction, what you want to do is you want to shield mechanisms from the vagaries of distributed state. Crazy things can happen. You need to deal with the state. You just don't want to deal with the fact that it's distributed. So there's a very natural abstraction that comes out of this, which is I would just show you the state. I give you a global network view. That's the state you needed to deal with. I'm just going to say, here's a graph. Here's the network. It's annotated with all the metadata you want. I'm going to give it through an API. And then if you want to use it, you now just program to that API. You're not writing a distributed protocol. You're writing a program over a data structure. Okay? So you're using Dijkstra, not Bellman-Ford. Now, as Martine noted, this is an oversimplification. I've described it as making it logically centralized. And you could. But the point here isn't that you have to make it centralized. It is that the distribution model is your choice. It's not the network's choice. You have hidden the distribution in the network. You now can distribute it based on scalability requirements or resiliency requirements, whatever you care about. But it's not based on the fact that I've got 10,000 switches out there and they all have the state that I've got to manage. Okay? So from now on, I'll just assume that it's logically centralized. The second abstraction is the specification abstraction. When I'm writing a control program, it should express my desired behavior. it should not have to tell you how to implement that behavior on the particular physical network you happen to be running on. So the natural abstraction is some kind of simplified model of the network that is only complicated enough to allow you to specify what behavior you want. Okay? So this really is network virtualization. You want to provide a virtual image of the network, let people control that, and then what the real physical network is underneath doesn't really matter. So let me just give you a simple idea of what I'm talking about here. Let's assume the physical network was this, some complicated topology, but I was trying to do access control. So what abstract model of the network would you give me? The abstract model is I'd give you a crossbar. Because if the behavior I want to specify is A can or cannot talk to B, I don't care about all these switches. For specifying the behavior, I just say A can or cannot talk to B. It's somebody else's job to figure out how to make that happen in the real network. And then the third abstraction is a forwarding abstraction. And here, obviously, the control plane needs to allow for flexible forwarding. It doesn't want to be limited. So the abstraction should not constrain the forwarding behavior, but it should hide the details of the underlying forwarding hardware. That is, if you're going to get beyond vendor-specific solutions, you don't want to have to worry about what particular hardware you've got underneath. You want some higher-level forwarding abstraction. So you've been very patient. And so at this point, I'm now going to summarize my entire talk in one sentence, which is that SDN is those three abstractions. That's it. Those three abstractions are exactly what software-defined networking is. No more and no less. It's a distribution abstraction. It is a forwarding abstraction. It's a configuration abstraction, and you are done. So SDN is not just a random idea. It can be derived in this loose metaphorical sense from decomposing the problem of network control. And what this does is it gives you some confidence, at least gives me some confidence, that there's some fundamental validity and general applicability. Fundamental validity because it comes out of these arguing about what abstractions you need. General applicability because in arguing about those abstractions, I never once mentioned what the control problem was. It is anything that's trying to manage network state that has to do with forwarding falls into this category. So fundamental validity, general applicability. Let me talk a few minutes about realizing these abstractions. Just that this will be showing the same pictures that you've seen 10,000 times before, but it'll give me some context for my later comments. So the core challenge is to make the distributed control problem a sort of logically centralized one. And as I said before, by logically centralized means the distribution model is my choice, not the network's choice. So to do so, I have to design a common distribution layer. That is, some layer that gathers the information from the network elements and then sends out control messages to them. And this is done, as we always say, by network operating system. And so here's the picture that we've all known and loved. You know, you start off traditional control mechanisms, you have these individual routers exchanging pairwise messages, but instead in SDN you throw those away, you define a network operating system which provides this global view, and I will say I stole these slides from Nick, so I don't know what he's going to give a talk on. And then you've got a control program over that global network view, and that can be routing, access to a rule, whatever it is. Now, the key thing to recognize is that this is a major change in the paradigm. We are not designing distributed control protocols anymore. We are defining a centralized or logically centralized control function, which is the configuration is a function of the network view that I use. And so as soon as that view converges, your configuration will converge. It's much easier to think about and much easier to reason about. So that means this spells the end for distributed protocols. But what is somewhat less appreciated is that this is the beginning of the software era of networking. And we all say software-defined networking, and yeah, we know that involves software. Software communities are different from us. They have different thoughts about what you standardize and what you don't. They have different thoughts about what a reasonable rate of change is. They have a very different culture. By adopting SDN, we have to become a software community. We're not anywhere close to that now, but that's where we're going to have to be. That was the first abstraction. Let me talk about the specification abstraction. Here, it's just a simplified model of the network. Control program is merely, when you give me this simple model, I then have to configure that. And then we have this layer that takes you from the simple model to the actual physical topology and says, if this is the behavior you want in the simple model, I have to translate it to the actual physical topology that the real network has. So that means that in this nice picture, you now have to kick up the control program, insert a network virtualization layer, so that now your control program configures the abstract network view. Your network virtualization layer takes that and configures the global network view, and then your network operating system actually communicates that to your physical devices. So now the SDN picture has gotten a little more complicated so that you can actually simplify the act of writing the control program. And that leaves the third abstraction, which is the forwarding abstraction. And here, you sort of think switches have two brains. They've got an ASIC and they've got a management CPU. And you actually, your forwarding abstraction has to consider both, because they're very different. Interfaces is CPU, management, who cares? We can do that 10,000 different ways. It's the ASIC abstraction, which is much more subtle, and that's where OpenFlow comes in. This requires a lot of careful thought. And I'm not going to talk any more about the details of the OpenFlow configuration, except to say the following. That when you say OpenFlow is the answer, what that really is assuming is that switches are the unit of forwarding abstraction. That's not necessarily true. You could say for a data center, for instance, I want the fabric. That is, the forwarding abstraction says I'm going to take it from one end and take a packet and deliver it to the other end. That's the forwarding abstraction. That we can build fabrics for data centers, and maybe that should be your forwarding abstraction rather than individual switches. I don't know which is right, but the point is they're both SDN. So I say that just to caution that we should keep in mind that as we debate the finer points of OpenFlow, that it's, as Martin noted, it's a detail in the overall SDN architecture. It's sort of down there and it occupies one small place. Because it is closest to the hardware, it is absolutely crucial for the industry. I am not diminishing its importance at all. We need to standardize it. We need to understand it. We need to get it right. But architecturally, it's a minor piece. And the only reason I make that point is we need to make sure that we don't let the tail wag the dog. And if the tail is OpenFlow, what's the dog? And the dog here is a clean separation of concerns. That is, in SDN, you have a control program that specifies the behavior on an abstract model. The only thing that control program thinks about is what does the operator want. That's it. You don't think about anything else. You then have network virtualization that says, I don't know anything other than I've got this abstract model that's been configured and I have to translate it into a real physical topology and figure out how to make that mapping coherent. And then you have a network operating system that says I have this fully configured logical map of the network and I now have to transfer that into the actual physical devices. Each piece of this architecture is a very limited job, something we know how to do, that doesn't involve the overall picture. Now, there are 2 points I want to make here. One is that, as Martin said, innovation is the true value proposition of SDN. And then going back to my second slide, the reason why the internet was so successful is because they had these layers of abstraction that gave you separation of concerns that enabled you to innovate in these separate layers at the same time in a compatible way. That's what SDN does. It builds this ecosystem that we can have progress going on in all of these pieces in a way that maintains an overall coherent system. That's the value proposition of SDN. So there's this tie between abstractions and innovations. It's very fundamental, and it is core to why SDN is the right answer. Okay, so in my remaining -2 minutes, let me just say a few final words. The future of networking lies in finding the right abstractions. You know, this era of defining a new control protocol every time you have a new problem, that's over. It's going to take years to internalize and evaluate abstractions. It's taken every other field, from operating systems and distributed systems, from the time they come up with their first idea to the time they sort of decide that this abstraction is right. It's going to take a long time. But what's going to take even longer is for us to adjust to the fact that software is king now. That it's going to be a software-oriented culture that's going to rule our field. And that's going to be harder for us to deal with. And lastly, we are in the early stages of an intellectual voyage. We should keep our minds open. that I know how far we've come in our thinking in the past 4 years, and if we go as far in the next 4 years, things will look very different than what we think now. They won't be different in the sense that we will think we were wrong now, we'll just think we were naive. And on that note, thank you.
Okay, so again, we have a lot of time for questions. At least whatever, 10 minutes or so.
Yes.
Richard Probst, SAP. So if these are the new principles that help us think about theory of networking in a new way, then they also apply historically. So you thought about what it would take to take some historical artifact like SMA and think about it according to these abstractions.
So yes and no. What I would say is that we haven't gone back to SNA because to some extent this is about control. But we have gone and looked at how you would apply this to the data plane abstractions that we've all sort of said, oh, those are great, we're happy with. And there, what the analysis says is those are great abstractions. They are lousy interfaces. And if you fix the interfaces, you could do, for instance, everybody says architectural evolution is impossible. It's very hard once you define IP to change it. That's just a fact of life. Bullshit. If we got the interfaces right, we could change IP in a day. That's what we got wrong. Because we passed, as an interface, if a first-year graduate student designed something where you passed a location through an interface that didn't need to know about location, we'd fire him or her. Well, that's what we didn't even know. We didn't know any better. But we're stuck with those design decisions. So yes, looking back historically, you can say that by not thinking about it in terms of abstractions and interfaces, we made some elementary mistakes. That if we fix them, we could do a lot better today.
With Wolfgang Riedel working for Cisco. And more a general problem. So it's more like, from my understanding, is this the right approach? I think it's more about identity, and I don't care about the IP address or the location or whatever. So it's like all the enforcement, all the forwarding should be based on an identity of a virtual machine, of a user, or whatever. So the question is, shouldn't a network just be smart enough to do a forwarding decision or policy enforcement based on identity or not on a programming interface? So do you really want to program networks for millions of users around the globe? Or shouldn't it just be a better solution that the network is intelligent enough to deal with these identities?
So I think it is always a dangerous step to take high-level semantics and expect low-level silicon to understand them, because sort of our high-level semantics doesn't stay constant for long, and silicon unfortunately does. So I think that the notion of identity is actually pretty subtle. And so the way we establish identity is typically through crypto and other kinds of things, and then sort of baking that into a low-level forwarding chip, I think would be a mistake. I think that you want your control program to understand identity at the software level, and then tell the forwarding hardware, I said this is okay, so go ahead and forward it because I understand the semantics. You don't, but trust me. So I do think that you want to bake it into the forwarding overall architecture, but you don't want to keep it out, you don't want to put it in the very lowest levels. And so SDN, as a way of being able to put it into your software infrastructure in a way that translates directly into your hardware, is exactly what, to some extent, what some of our team's early projects were trying to do.
Yeah, I agree on the ASIC level. It's more like from a point of how you will approach the solution. And this is the point where I think, so I just remember the talk we had yesterday that we expect in the future that network operators are programming their network topology in Python. And I think it's the question if we really expect people to program networks in Python, or the network should just be smart enough that I don't have to program the network. That's the question.
So I don't want to be argumentative, but it's my nature. That somehow, when you make a network smart enough, you are programming it. And the only question is whether you expose it to your company or expose it to the world as a whole. That programmatic interface. And I think that's really the only difference.
Dimitris Styliadis from Andalusia. I have two, if you want, comments, questions. The one is, abstraction is good, and I love it, but it's also a little dangerous. Because if we take, for example, a Ruby on Rails programmer, he has absolutely no clue how to optimize a program for the hardware, right? So I need gigabytes of memory today to write the same Microsoft Word document that I would have written 10 years ago with a couple of megabytes in later.
Right.
So that's one thing, and how do I avoid this trap? My second thing is, does the abstraction need to go all the way to the forwarding element? Why can't we get, for example, an OSPF area and call it an abstract model of a black box and deal with it at the edges? Why do we need to go on every forwarding element?
So let me go to your second one. Yeah, absolutely. I mean, when I brought up the idea of the fabric being the forwarding model, yeah. I mean, whether or not that's where history goes, but I think that would be perfectly fine. For the abstractions and the performance issue, I think it really is, the reason why we have people doing Ruby on Rails is because for that area, it is the speed of development is more important than the speed of execution. That's probably not going to be true in networking.
Exactly, because you have abundance of resources, right? The abstraction is very easy when resources are abundant.
But the problem, it is not so much that the abstractions are so bad, is that you let people program it who don't care about performance. And my guess is the people who program networks, their employer will care a lot about performance because that's what the customers will care about. So this gentleman brought up, we probably will program it in Python, but that Python won't be on the fast path. It'll be setting up the state, which then can run at fast speeds.
Tyson, Verizon. Is there anything we can learn from applications, operating systems, and database principles such as naming and addressing that we need to adopt in networking and the abstractions you described? You gave the location example that's a problem with IPs, or something do we need to relook at some of these basic ways we identify objects in these abstractions as we evolve? So
I think there are two separate ways that I think when you talk about the overall internet architecture, I think absolutely. When you think about sort of SDN, which is typically thinking about sort of managing one sort of a network under one domain, there we don't have to have uniform agreement on what identities mean, and sort of that domain can decide whatever it wants to think about identities. And there, I'm not sure whether there are universal lessons to be learned. But I think certainly when you go to the overall internet architecture, you need to think about a global naming system that applies everywhere. Then we need to think about what other disciplines know.
A comment and a question. So the comment first. If we like driving stick shift, that's because we like performance, and not because we like complexity.
I would actually argue with that, but
sure.
Driving in Palo Alto, driving a stick shift, how much performance does it get you? I can beat you to the next stoplight.
That's because you're driving in Palo Alto. So the question is that if OpenFlow is a small piece in that SDN picture, what are the other large pieces that we should be working on?
Well, no, so I think we are working on it. Sort of the network operating system, I think the structure of applications on top, it's sort of all those things that work is going on. I think the difference is OpenFlow is something we have to standardize so that we all in this room have to agree on. Network operating system, different people can program it different ways. We don't have to argue to convince each other. You build yours, I build mine, we take a speed test, see who's better. We don't want to do that with OpenFlow because we want everybody to have a uniform standard. So it's sort of fundamental for the industry, but it's that's not the sort of heart of the architecture, it's the heart of what needs to be standardized.
Greg Papadopoulos, NEA. Could you just reflect a bit on how we keep from making the same mistakes that we did in the computing side in terms of people controlling APIs? So the OSs, it started from OS 360 and moved out into a bunch of different areas. We took a few decades to get it into, say, Linux. It looks like the mobile OSs are similarly moving out, and who knows what will happen. How do we prevent that from happening?
It's a great question. I can't give you a definitive answer except to say that we hopefully should get some open source versions of these interfaces available, and so that we soon develop the Linux of the world so that nobody is blocked out. People may still go after their proprietary solutions, but if you don't want one, there is a sort of open source version available. That would be my initial thought, but I don't have anything deeper than that. I don't know who's first, so I think he's here first.
Great speech, very exciting, I must say. I have two questions. I heard like controllability, manageability, automation from yesterday's on, but are we also addressing a capacity problem on an internet scale?
Capacity problem,
Like they're talking about data explosion. I didn't hear much about the capacity other than the controllability.
Yeah, so I'm not the right one to ask about this. I would assume that people who know much better than I would answer that, if this approach makes it easier to build fast hardware, then that's the way we address the capacity problem. We're taking some of the complexity off the data path, moving it onto the control path. But I don't think we fundamentally don't increase the capacity directly. But actually, I would say the networking industry has been pretty phenomenally good at providing high-capacity components.
Probably a related question is that in your final words, you said era of new protocol.
Yeah, protocol per problem.
Yeah, so you mentioned verbally control protocol. So is there a need for a new set of data plane protocols? For instance, replacing internet protocol.
Oh no, I'm sorry. No, there's not. It was more that in the data plane, we haven't invented new protocols every time we have the new problem. I mean, TCP is very widely used, HTTP is very widely used. We're very good at reusing there. On the control side, we haven't been as good. But I think we'll reuse on both now, as opposed to inventing, sort of ad hoc invention on the control side.
Hi, Derek Silva from Infotech Research Group. On a more practical day-to-day level.
Then you need to talk to Martin.
And I thought so. Maybe Martin can come up and answer this. Like, what does this mean for a network admin who's maybe rebuilding or building a brand new network, or is bringing in OpenFlow and some SDN components and putting those on top of the network in terms of what's still being done at the switch level and what's being done?
So I was joking the first time, but I actually do think Martin's the right person to answer this. You want to take that?
Sure. Can you turn this on here? So I think it's just really important to remember that, OpenFlow is for system builders. And it's not actually for end users of networks. And so the way that you evaluate how OpenFlow helps you is to evaluate the products that are built on it. And these products are going to be totally different from each other, but they can look very similar to existing components you have today. So for example, people are building BGP routers that look, smell, taste, and run exactly like BGP routers, but they're running using OpenFlow on top of merchant silicon. So there's nothing different about that. And so, I don't think that the question we should be asking is, what does OpenFlow do for random operator X? It's like, what can third-party Y do to provide something new? And I think that this is the question we're going to answer in the next couple of years. Is that fair? Yeah. Thanks.
Take the last question, maybe, or okay, go ahead.
Pushan Kanekar, I'm from Cisco. I have a question, maybe.
Yeah, Martin.
So basically, what I understand is essentially a lot of the abstractions, whatever you have talked about, inside a switch or a router, a lot of it happens, but those are only available to that company. So it's essentially a vertically integrated stuff. What you're trying to do is essentially make it horizontal. It's a great way, but that now leads you to, and to give an analogy, say on a Microsoft model, on the hardware comes from Intel and a bunch of other hardware. You've got Microsoft's OS running on it, and you've got a bunch of applications. You've got VMware somewhere in the middle. But the issue with that today happens is if your PC crashes, who do you go and find? Is it the application's fault? Is it the virtualization's fault? Is it the hardware problem? Or is it your OS problem? Now, today in networking, because it's vertically integrated, if a router fails, you go catch Cisco or Juniper, Brocade, or whoever is hardware. With this horizontal model, suppose you have the Nicira controller controlling the NEC switch, and network doesn't work. Where do you think the operator whom should the operator?
This year. No, sir, I mean, there will be the people who sell these systems will have a well-understood chain of debugging and who you contact first, and that'll be part of how the market develops. I said that somewhat facetiously, but I actually think it's the right answer, which is you probably start with the people who provide you with software. They'll have the much best understanding of the system overall, and then they will be able to isolate whether it's a hardware problem or not. But I mean, the problem you raised is a real one, but the market will solve it. Okay. Meaning that people will buy vertically integrated if this is such a serious concern they can't get good answers from other people. And some people buy Apple, some people buy the Microsoft on top of Intel, largely for this reason, depending on how much they want to just go to a sort of a genius and say, fix it, I don't want to understand, or they want to debug it themselves. But this gives us the option, but the concern you raise is a valid one.
Okay, the last question.
The last question.
Yes, it does. Neil Swartz, Unit Networks. So I think one of the major challenges that most of the people who use our equipment and everyone else's equipment in this room is not necessarily one of optimizing what's already there, but figuring out how can I monetize information that I have in my network, availability, and bringing new APIs to the application developers so that their network becomes sort of more valuable to end users, or the information that's there more valuable to end users. Would you say that SDN, as in software-driven networking, is a good step in the direction of software-defined networking to get us from this notion of hardware-centric and box-centric to a more software-oriented world?
I didn't understand most of your question. I mean, the distinction between software-driven and software-defined, I honestly don't know what you're driving at.
What I'm driving at is today, carriers have a challenge of basically running their network and actually making money off of that network. A lot of information is available inside those networks today that can be used to monetize their existing infrastructure. Getting from where they are right now, where that information is locked inside of a network device, to a point that they can expose and monetize it, will take a few steps. Going from where they are today to an entire software-defined infrastructure also takes a number of years, as you mentioned. Is software-driven networking, as in one where network equipment talks much more intimately to applications, and applications talk much more intimately to networks, is that an intermediate step that you would suggest in this path towards SDN?
No, I think it's actually the wrong step. Meaning, I would think that having networks that sort of provide, for instance, a very familiar interface right now, but underneath are much more flexible, is going to lead to much more rapid adoption. And then we can start learning to use the much more general features of them, rather than doing it the other way around. So that, in other words, I think that some of the early uses of SDN are basically to say, I'm going to take this big, expensive single switch, I'm going to replace it with a bunch of smaller switches, and create a sort of a virtual BGP router. I understand how that interacts with the rest of my network, so I'm not really changing the rest of my network. I've just changed this one component, and I've built it in a way that's cheaper, more flexible. That, I think, is just the easier deployment path. Whereas sort of monetizing all this information that lies in my network, that's sort of a larger sort of institutional change that while I think it's great, is not where I would start.
Thanks.
Okay, with that, let's thank Scott again. So we are going